By 2050, the aviation industry is mandated to meet strict greenhouse gas reduction targets. Reaching these emission goals demands transitioning existing fleets toward more electric, hybrid electric, and eventually all-electric aircraft. Implementing this transition requires new hardware architectures. Urban air mobility vehicles and vertically launching airframes rely on distributed electric propulsion to generate lift and maintain stability. For decades, engine certification has relied on a standard known as CSE Amendment 6. The parameters of that standard were engineered for the thermodynamics and mechanics of internal combustion and turbine engines. Those combustion parameters are inapplicable to eVTOL airframes powered by distributed electric arrays. CSE Amendment 6 does not account for propulsion batteries. It lacks the regulatory language needed to evaluate complex electrical interactions, high-voltage distribution, or the failure modes specific to battery-powered flight. To bridge this gap, the European Union Aviation Safety Agency developed Special Condition E-19. This document is a first principles regulatory framework designed to govern electric and hybrid propulsion systems. Deploying next-generation aircraft safely means engineers must rebuild the mathematical boundaries of propulsion safety from the ground up. SC E-19 defines an electric or hybrid propulsion system as the complete chain of components generating lift, thrust, or power for the aircraft. This diagram illustrates an EHPS architecture. The regulation breaks it down into integrated subsystems, mapping out the electrical power generation, internal wirings, integrated cooling systems, and power management controllers. Power flows sequentially through these nodes. The controllers regulate the voltage, routing it into the electric engine, which then transfers mechanical torque to the propeller or rotor. SC E-19 outlines a strict regulatory distinction regarding energy storage. An isolated propulsion battery is only considered part of an EHPS when it is associated with an electric engine providing power to a thrust device. Structural batteries introduce a distinct engineering challenge into this system. Because they serve as both active electrical power sources and load-bearing physical airframe components, they must be validated for both electrical stability and mechanical stress. SC E-19 eliminates isolated component design. Every electrical element is treated as a critical flight system, necessitating a holistic approach to type certification. Operating an electric array requires engineers to establish rigid operating limitations based on electrical performance data, which must then be approved by the agency. This thrust-to-time performance graph visualizes those required thresholds. Engineers must define the rated maximum continuous power for unrestricted duration and set a specific ceiling for the rated takeoff power used during departures and discontinued approaches. If one subsystem suffers a thrust loss, the remaining subsystems must instantly compensate. The data plots this as an emergency rating, the power output required to offset the failure of an adjacent unit. The limits distinguish between anomalies. A normal transient EHPS exceedance is a brief, intentional power spike designed to ensure aircraft stability. An inadvertent exceedance results from abnormal operation or system failure. Governing the rapid flow of current and voltage requires temporal and thermal rating constraints that operate on milliseconds, distinct from the steady-state consumption metrics of traditional jet fuel. Section EHPS.80 mandates a system-wide safety assessment. To establish the probability of failure conditions, engine manufacturers must calculate these fault rates in direct coordination with the aircraft manufacturer. The assessment relies on strict definitions for critical parts, primary failures, and secondary failures, treating localized errors as links in a larger failure chain. The objective of this assessment is isolating and preventing hazardous EHPS effects. Engineers must prove their designs will not result in the release of high-energy debris, significant reverse thrust uncommanded by the pilot, or uncontrolled fire within the system. The assessment also targets severe environmental and electrical hazards to the crew, requiring strict safeguards against toxic cabin air, electrocution, arc blasts, and excessive electromagnetic fields. Under this regulatory framework, a localized electrical fault is evaluated as a potential catalyst for an unrecoverable, catastrophic aircraft failure. Theoretical safety metrics must be physically substantiated through extensive endurance, durability, and operational testing. EHPS.470 dictates physical demonstrations for rotor locking. If the design utilizes a mechanism to prevent continued rotation, it must survive repeated locking and unlocking operations to prove absolute mechanical reliability. The physical thermal testing is equally rigorous. For any declared short-duration emergency rating, the subsystems must prove they can sustain operations at their absolute temperature limits, plus a built-in safety margin. Once the physical design is verified, the manufacturer must finalize a service management plan. This ensures all critical parts are maintained and repaired to the specifications of the original engineering plan. EASA certification legally binds the physical hardware to a continuous lifecycle of documented maintenance and airworthiness. When brought together, this entire framework integrates the architecture, the power ratings, and the safety assessments into the physical structure of the airframe. Swapping jet fuel for batteries requires re-engineering the mechanics of flight. The electrical connections, thermal loads, and structural forces operate under distinct physical laws, demanding an integrated approach to system design. Regulatory structures like Special Condition E-19 provide the mathematical rigor required to move experimental aircraft off the test stand and scale them into commercial airspace. By establishing these foundational principles of electric propulsion safety, the aviation sector gains the structural blueprints needed to safely pursue zero-emission flight.